Okay, a portable basketball set has a base and a post arrangement. The post arrangement consists of a post, backboard, hoop, and net. The base can be filled with water to increase stability. Okay, the maximum weight of the base is about 810 Newton, and the weight. Okay, the maximum weight of the base is about 810 Newton, and the weight of the post arrangement is 26 Newton. The basketball set may topple over when the wind blows due to the large area of backboard. So we can say the wind is blowing on this backboard, yeah, on backboard, and this is the weight of the base. Yeah, they put water. They put water onto the base to make this base heavier. Yeah, to make this heavier. And we can see this portable basketball set has an axis of rotation at here, the point of contact to the ground. Yeah, it has point of contact of the ground, so it topple over this axis of rotation. All right, so we can determine the minimum of force of the wind. Okay, this is the whole questions. Yeah, determine the minimum force of the wind that will cause the basketball set to be blown over when it is at the angle shown. This angle 15 degree is the angle when the wind blows over the basketball set. So the basketball set will fall over at this angle 15 degree. Yeah, okay, maybe make it okay. So ignore the effect of the wind on the base. Okay, the wind has no effect on the base. Yeah. So okay, first of all, we want to find what? We want to find the minimum force of the wind. We want to find Fw. Okay, this is our target. We want to find Fw, the force of the wind. So first of all, we draw. This is a rigid body. Yeah, this is a rigid body. We are talking about topple over. Yeah, that means topple over. So we are talking. You see the keyword here, topple over, means this is about rotational motion. Okay, this is about rotational motion. So this is not just a particle, It's a rigid body. It's a rigid body. Yeah. Hold a second. Okay. So how to draw? How to do this question? So first of all, we draw free body diagram for the whole rigid body. Okay, for the whole rigid body, we draw a free body diagram. So this is the free body diagram I got. Yeah, this is the this is the post. This is the base. Right, 15 degree, and this is the axis of rotation here, and this is the weight of base at the center of it. Okay, this is the weight of the post. Yeah, the weight of the post arrangement. It's not at the middle. Yeah, it's actually slightly on top of it. Why? Because at the top here has a larger mass. Below here less mass. Top here more mass. So it's called uneven. Yeah, this post is uneven. That's why the weight of the post arrangement is slightly on top. It's not at the middle. Okay, because this rod is uneven. Yeah, uneven. So it's over here. Okay. And then this is the force of wind blowing at this side. Okay, so this is a simple free body diagram I have drawn. Okay, I label down all the values here. So what you have to do is this is about equilibrium already. Yeah, equilibrium. So you can use total torque equal to 0. Yeah, to do these questions. But first of all, we need to how to check the torque. Okay. You need to resolve all these forces to perpendicular to the moment. You see, this force is not perpendicular to the moment. It's not perpendicular to the distance. So you have to resolve this WB, the weight of the base, the weight of the post, the force of the wind to perpendicular component of the distance. Okay, so this is how I resolve. So first of all, you draw the axis. You draw the parallel and perpendicular axis. I have drawn already here. Okay, so you can see I draw a perpendicular axis here. So for the weight base, I draw a perpendicular axis. For the weight of the post, also I draw a perpendicular axis. For the force of the wind, also I draw a perpendicular axis. So we can see the weight base can be resolved into two components. Each of these force can be resolved into two components. One is parallel, one is perpendicular. Parallel, perpendicular. Parallel, perpendicular. Only, you see, I highlight only the perpendicular component. I only highlight the perpendicular component. You know why? Because the parallel component has no torque, does not cause any rotational motion. So we can say the parallel component can be ignored. There has no torque. The one have torque is only the perpendicular component, which is this one, the highlighted one. Okay. But to resolve all these forces, I need angles. So how do I find the angles? This one I just look at the angle. I draw this line here, and then we know that the weight of the base. Let's look at the first part, the first force. Okay. All right. Okay. Look at this one. Okay. So first you look at the weight. Okay. This weight directly downward. Okay, this weight directly downward actually is the same line as this one. You see that? These two lines, they are parallel. Another parallel line is this one. You see, this one perpendicular line. This perpendicular line is also parallel to this one. Parallel to this one. So we can get an angle for this one because this angle, the angle given, actually it is the same angle with this one. It's the same angle. So this angle is the same as this one. It's the same angle. Okay. So we can resolve this force, the weight B, into parallel and perpendicular component already, and we just use the perpendicular component. Okay, we just use the perpendicular component. Okay, then now we look at the weight of the post. Okay, look at the weight of the post. Okay, this one also can resolve into two components. Okay, the parallel and perpendicular component. Okay, so again, this angle, the angle over here is the because this weight is also parallel to this one. You see not? This line is parallel to this one. Okay, so this angle and this angle, they are corresponding angle. So this is also 15 degree. 15 degree. So we can resolve the weight of the post already. Parallel and perpendicular component, and we just use the perpendicular component to find the torque. Okay, the parallel component has no torque. Has no torque. Okay, I thought about this already in the previous video. Okay, done. Now look at the force of the wind. Force of the wind also we can resolve into two components, the parallel and perpendicular component. And what's the angle? This one a little bit tricky, but it's not so tricky. It's not so tricky. Look carefully. Oh my god. Okay, look carefully. Look carefully. This line, what can we say about the lines? I make a line here. Okay, this is the. Okay, look again carefully. Okay, we notice that I draw another line here. You see this vertical line is parallel to this one, isn't it? Parallel. So we can see this angle. Okay, this angle, okay, is 15, the same as this one. So we can find this one. This one is 75 degree because it's 90. Because this perpendicular axis. Okay, 90 minus 15, you get 75. Here get 75, isn't it? This 75 is the same as this 75 here, isn't it? Because this line and this line, they are parallel. See not? This line and this line, they are parallel. So this angle is the same as this angle. Okay, so we got this here angle 75 degree. 75 degree. So here you see this line is vertical, and this force, the force of the wind, is parallel. If you look over here, this force of the wind is parallel, right? It's parallel. So we can say the parallel line and perpendicular line, they are 90 degree. 90 degree. So again here 90. So minus 75. minus 75, get here 15. So we got the 15 degree, 15 degree here. So we have the 15 degree here. So we can use, we can find the component already, the parallel and perpendicular component, and we can resolve already. And we just use the perpendicular component to find the torque. The parallel component has no torque. Okay. Finally, this is the perpendicular component which really matters. Yeah, you see this perpendicular, 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 all 90 degree to the distance, or we call it the moment. Okay. All right. And this is the distance. Yeah. This is the distance R1, this is R2, and this is R3. Try to find out what is this distance, okay? Because we are going to use this R1, R2, and R3 to find the torque 1, torque 2, torque 3. And this is F1, this is F2, this is F3. So to try to find, okay? So try to find torque 1, torque 2, torque 3. Yeah, try to find all these torque. Try to find all these torque. Okay, then you can apply the total torque equal to 0 to find the whatever, yeah, to find the FW, to find the FW. Okay, so that's how we do it. Yeah, remember we have this one is clockwise direction. It turn this whole thing clockwise. Torque 3 is clockwise. Torque 1 and torque 2, they are turning this whole thing anti-clockwise. So we can use turning clockwise torque is negative, turning anti-clockwise torque as positive. Negative torque for clockwise, positive torque for anti-clockwise. So apply that positive negative to the direction of the torque, and then apply total torque equal to 0, and surely you can find the force FW. Okay, and then what will happen to the B? If you fill the base with the sand instead, of course you increase the weight of the base. Yeah, increase the weight of the base. If you increase the weight of the base, of course you will increase this torque 3. You will increase the torque. You will increase the torque clockwise. You will increase the torque clockwise, and so you explain what will happen later on. Okay, that's all for this question. All right. Yep. That's all for this question.